discussion during the recess break also for all of you who have more questions. Next, I'd like to introduce Ellen Bard from University of Texas at Austin, and he will be presenting detection of short-lived electrode reaction intermediates with the scanning electrochemical microscope.
Oh, thank you. One of the great pleasures, as any teacher knows, is to see an ex-student do very, very well. And that's what I'm seeing today with Dick. We go back a long time, now as colleagues in the same department. And it's been a great pleasure all these years. Not always smooth sailing every day, but a great pleasure to work with Dick and to see him become so successful. What I'd like to talk about today is it's a little bit of an advertisement for scanning electrochemical microscopy, but I'd also like to talk about finding intermediates in reactions, understanding reaction mechanisms in electrochemistry, which has been a very active field in electrochemistry for many years, and particularly to go back to a very old problem, which is, are there two electron transfer reactions? Can one transfer simultaneously two electrons, as we see in the table of standard potentials and so on? And so those are the kind of questions I'd like to address. And so I'll talk a little bit about the idea of intermediates and reactions. Then we'll talk about the favorite technique for looking at mechanisms, cyclic voltammetry, but what the problems are. Talk about scanning electrochemical microscopy, which eliminates some of those problems. Then talk about these two electron transfer reactions and give a particular case that I've been looking at since I was a graduate student, believe it or not, of tin 4 plus 2 electrons goes to tin 2, and to try to convince you that, in fact, we find tin 3, that it goes tin 4 to tin 3 to tin 2. So what's an intermediate? In this slide, B is the intermediate. In other words, I have an electrode reaction. Some species A gets reduced to B, but B is not stable. In a famous EC reaction, B disappears. And so B has a transient existence depending on the rate I'm making it and the rate it's disappearing. And I would like to find B as an intermediate. In the more specific case that we'll talk about, we have what's called an EE reaction, where A goes to B, but B is easier to reduce than A. So as soon as you make B, it's going to disproportionate to A and C and also reduce to A and C. And so B in this case is also an intermediate. And if I want to understand these reactions, one of the best ways is to find this guy, find the intermediate. Now, the principle is that if I have an EE reaction, it's always should be always more difficult to do the second electron transfer step. In other words, if I have this, I'm adding an electron to a neutral species here, and that makes B minus, and so there's some potential here, some driving force needed to push that on. But the next guy, I have to add an electron to a negatively charged species, and so that's going to be harder. And it's the same rule about removing electrons. If you go in the gas phase and look at ionization potentials, the first potential to remove the first electron is well known. The second electron is much harder, by something like 5 eV, to remove, because I'm pulling that electron out of this potential field of the plus species. And so one has to ask, why is it then that I can see A going all the way to C in what looks like one step in many reactions, as we'll show before? And so that's kind of what we're asking. So the favorite way of looking at these kind of reactions is by cyclic voltammetry. And in cyclic voltammetry, as everybody in this room knows very well, you scan the potential up, you scan the potential back, and you can see the back reaction. And if there is this kind of EC reaction, then you have to compare the effective scan rate, RT over F, which is kind of 25 millivolts, over V, the scan rate in millivolts per second. So this has dimensions of seconds, volts over volts per second. And I compare that, that's how fast I'm going up and back here, to the lifetime of the species, which is generally, if it's a first order reaction, K is the rate constant for this reaction. And so that has dimensions of seconds to the -1, so this is seconds. So I compare here the lifetime of the species, B, to the rate at which I'm trying to address it back and forth. And so you can see if you scan at a high rate, you can see the back reaction. I capture the B here. But if I scan slowly, I just get this irreversible wave, and B is gone. And so if I want to look at a more and more unstable species here, I have to scan faster and faster and faster. And the limit of finding a species with a very short lifetime is how fast can I scan. And here are the same kind of things really calculated. So here's different scan rates for unstable material. And so fast scan rate, I get a nice cyclic and I capture it, slow, and I get this irreversible wave. There is a problem, however, in fast scan cyclic, which everybody knows who does this. And that's you're always competing with two things: capacitance. In other words, when I scan, I also have to keep charging the electrical double layer. And surface reactions. If I, say, oxidize platinum to platinum oxide, gold to gold oxide, or I have other surface reactions, I also have those going on. And the difficulty is that whereas solution reactions go as the square root of scan rate, surface reactions are proportional to scan rate. And so as you increase the scan rate, surface reactions become more and more important. And eventually, if I start going to what people talk about 1,000,000 volts per second, I start to see a big loop of capacitance with a tiny bump of all the stuff going on in the solution reactions. And those are very hard to analyze. One has to be very careful to subtract out the background and then try to find it and so on. So it can be done, but it's very difficult. So it can be difficult even with very small ultramicro electrodes. And here's a picture of that. So here's at a slow scan rate. This first part, is this thing showing up? This first part is the capacitance in here, and then this is the solution reaction. But as one increases the scan rate higher and higher, the capacitance of the surface part goes way up, and the solution part gets very small. So if I did this as a cyclic voltammogram, I'd have a big loop over here of surface waves and only a little bump on top of it, which is the solution one. And this will be the problem of any transient electrochemical reaction. However, if I do this by scanning electrochemical microscopy, and I'll discuss it very briefly in the next few slides, then things change, because in scanning electrochemical microscopy, I'm looking at steady state reactions. It's not a transient technique. I look at the limiting steady state current. So all capacitance effects, all surface reaction effects disappear. They're not relevant in SECM. Well, then you say, if they're not relevant, how do I get time? Well, as we'll see, SECM involves the transport of a material between two electrodes. And that involves the distance between two electrodes, d here, and the diffusion coefficient. And as everybody remembers, d squared, centimeter squared over this centimeters squared per second is now seconds also. And that has to be small with respect to the rate of the reaction. So I can get my time variable as a distance variable. That's always the case in electrochemistry. And if I make a distance between two electrodes small, even at steady state, I have a very, very short time that I can look at. And the limit here is not capacitance or surface reactions, which don't come into it. The limit here is how closely can I space two electrodes and know that distance. So let me try to explain in a very quick time what's going on in SECM. So, as everybody remembers, if I take an ultra-micro electrode, an electrode with very small dimensions, nanometers to microns, which was pioneered earlier by Fleischmann and then by Mark Whiteman, Christian Amator. A number of people have done a lot of work in this. When I switch on a very small electrode, I get a current transient like at any electrode, but the current transient very quickly goes to a steady state. And so in most of the reactions at ultra-micro electrodes, except when you're trying to scan them very fast, I'm looking at just the steady state current. And if I'm at the limiting current, this is this very well-known equation, 4N of dCA. This is the steady state limiting current here, which is a function of the radius of the electrode. And the rate at which it goes to the steady state is also, it's of the order of a square over d. And so it also, the smaller the electrode, the faster you get to the steady state. And so this is what happens at an ultramicro electrode. What SECM does is it says, let's take that same ultramicro electrode, but let's move it closer to another electrode or to another surface and see what happens. And so let's take three cases. I have my ultramicro electrode here. I'm going to move it down to a substrate. This is the electrode where it's very far away, and so that's the equation we saw before. That's just a steady state current at an infinite distance. But now, if we ask the question, what happens when I move it down to a surface? If the surface is an insulator, then as I move this electrode down, I block diffusion coming into that electrode. All of this is the diffusion, radial diffusion from around the electrode. But as I come down here, I cut off that radial diffusion path. So whereas in the bulk solution, I get my steady state current from this equation, as I get closer and closer, it goes down. On the other hand, if I take my ultramicro electrode and have it over a conducting substrate so that I can apply a potential here to regenerate what I'm doing here. In other words, I do a reaction here and then I do the inverse reaction here, or I do a reduction here and then oxidation here. I get what we call positive feedback. This guy diffuses back, so it's not only the stuff coming from the side, which is coming in and being blocked, but there's a feedback loop in here. And so here I have the same current in the bulk solution, but as I go closer and closer together, the current increases. And so I get this positive feedback effect. One can see that here in a typical experiment. Then if I have, let's say, an insulator and I move it closer and closer down, I get this. If I have a conductor and I move it closer and closer, I get that positive feedback. Now one can analyze these. These are calculatable very easily nowadays by straight electrochemical calculations. And what's very nice about it is if it's made as a dimensionless plot, if you take the current and normalize it by the current at infinity, so I over the current at infinity, that becomes dimensionless. And if I take the distance d and normalize it by the radius of the electrode a, that's also dimensionless. So in fact, these two plots, the positive feedback and the negative feedback plots, are universal plots. They don't depend upon diffusion coefficient, concentration, or anything else. If the current doubles when I get from here to here in distance, that's always at the same relative distance to radius. So these can always tell you absolutely, and depending on how well you can make the measurement, with a very good precision exactly where that tip or distance is. And that's important because that's the D that appeared in the earlier slides that shows the distance between the two electrodes as it diffuses in. This is just it's just a schematic of what an SECM involves. It involves usual electrochemistry with electrodes, but a means of moving this electrode with high precision up and down as you do in other scanning probe techniques. This is just a commercial one. Now, what's interesting is you can do this tip generation substrate collection, which is what we're going to talk about today. And so, in fact, if I have now my EC reaction, and I go A to B, and B is going to C, what I see on the substrate depends upon the distance between the electrode and the substrate. And this is a typical configuration where this is the radius, and this is the distance, and we're assuming that that's about 1. And so if this electrode is far away, then when I make B, none of it reaches the electrode. It is destroyed as it's coming down the line here to C. But as I move the electrode closer and closer together, more and more of this will diffuse to the substrate. And if I got it really, really close compared to the rate constant, I'll collect it all. I'll get 100% collection efficiency. So in a sense, if I measure how much of the product I collect, I can get an idea of the rate constant of that, and I can find this intermediate, B, and its electrochemistry on the substrate. So let's now start talking about two-electron reactions. And so, as I say, if you go into the table of standard potentials, there are many, many reactions written down, sometimes written this way: tin plus 4 plus 2 electron goes to tin 2 plus, or thallium 3 plus goes to thallium 1 plus. These are interesting because they're all solution reactions in presumably outer sphere. Some of the most important ones, like iodine going to iodide or chloride and chlorine, are two-electron reactions. That is, we write chlorine, Cl2 plus 2 electrons go to 2 chloride. Now, there's a lot of kind of fictitious understanding in here. One is this one, tin 4 plus 2 electron goes to tin 2 plus. Tin 4 plus, assuming that means the aqua ion, doesn't exist. I spent a year as a graduate student trying to make tin 4 plus in perchloric acid, and you can't make it. It hydrolyzes. You have a 4 plus species, it's going to take water like a son of a gun, throw out protons, pick up the hydroxides, and precipitate. And that's what happens. And so this really is always some halide salt or complex ion. It's not the free ions. It's the same with this. So we're really not doing that, and that gives us a means of compensating for the charges I'll show you. So really, the reaction I'm going to show you is this one. It's tin 4 Br6. That's the complex ion and high bromide concentration. Be the same with chloride. And the overall reaction is 2 electrons going to tin 2 Br4. You have a structural change, plus 2 bromides thrown out. Now, why is that important? We call this ligand-coupled electron transfer. It's similar to what's very popular now called a proton-coupled electron transfer. It's the means by which I get rid of this negative charge. In other words, if I start with this guy, SN4Br6 2 minus, and I add an electron, it immediately gets more highly charged. However, what it's going to do is throw out a ligand. It'll throw out the bromide, lose that negative charge. Now I'm ready to add another electron, I'll throw out another bromide, and go to that. That's the same as in a proton-coupled reaction, where you add an electron, a proton immediately comes on and neutralizes that charge, and so you go through all those coupled reactions. The reason we're in it, and because who've sponsored this research, is because we're trying to make redox flow batteries, I have to admit. And a redox flow battery, remember, is just a regular battery where the redox reactions are both components in solution. And again, I studied these reactions for a long time when I was a student. It would be very nice to have a redox flow battery that has a 2-electron process because you immediately double the capacity. And this would be the negative electrode. Bromide-bromine would be the positive electrode. These can all be done in one medium without any membrane. And so, in fact, this is an interesting but has problems as a redox flow battery. So let's look at this tin 4, tin 2. It's the same thing. If I was going to do it by CV, I would have to do it by comparing now. The reaction that happens here is really tin 4 plus an electron goes to tin 3 as the bromide salts. And then this disproportionates. So it goes to tin 2 and tin 4. And so this is really a second-order loss, as one can see when one does the simulation. And so now I'm not comparing to 1 over K. I'm comparing to 1. This is a second-order rate constant. Moles to the -1, seconds to the -1. So I have to multiply by molar here in both cases. And this is the key issue in SECM. To get the electrodes close enough, make D small enough that this is smaller than 1 over K concentration. So if I look at the CV of tin bromide, SNBr6, this is it. There's a reduction wave here, which is tin 4 to tin 2. And then there's no wave back here. In other words, I don't see any intermediate back here. But then I get another wave here, which is tin 2 to tin 4. It's a not reversible reaction in the sense. If I look at the scan rate dependence of each of these waves, it's perfectly v to the half dependent at this electrode. So it's clearly looks, if you're the first one looking at this, like 4 goes to 2 and 2 goes back to 4. It's a 2-electron transfer. Now, if you want to prove what the electrons are in those reactions, a nice technique is to take an ultramicro electrode and do a potential step to the tin 4 or do a potential step to tin 2 to tin 4 or tin 4 to tin 2 and look at the transient that I talked about in the wave about UMEs. So this is the transient. If I do a potential step to reduce tin 4 or oxidize tin 2, I get this fast transient. What's interesting about that transient is that there are 2 zones of behavior. At the very short time, it's behaving just like a big electrode. It's giving the usual mass transfer controlled reaction. And then I reach this steady state. And it's interesting if you simply plot the current at any time divided by the limiting current, you get the straight line plot. And as shown in this paper, I won't go into the detail, that allows you to determine the diffusion coefficient of the species independent of concentration or any other variable. In other words, N of the reaction doesn't come into this. They all cancel out when you do this ratio. And so I can get the diffusion coefficient. Once I get the diffusion coefficient, I can go back into the equation I showed before and get the number of electrons. And so if you look at this, I can get the diffusion coefficient, and in both cases, the number of electrons in the reduction or the oxidation is very precisely 2. So it's 2 electron reduction, 2 electron oxidation. However, if you look more closely at faster scan rates, so now I'm at a faster scan rate than the one I showed before, the waves are not so nice and clean anymore. And if you look at these, you see all of a sudden there's this funny guy has popped up here on the reduction side. And if I scan faster and faster, this is going to be bigger and bigger and bigger and bigger. And there's this very sharp wave that's popped up here. These are surface reactions. I don't want to go into all the details about them. But what this is is under potential deposition of tin. So in this crazy way, I'm making tin 4 to tin 2 on gold. But as Stan Bruckenstein studied, and we study later, there is tin 0 likes gold better than it likes tin 0. And so although the next wave, the wave of tin 2 to tin 0, is over here on bulk tin, there is a monolayer of tin that forms within this wave, and that's called UPD. And similarly, the tin 2 has an absorption wave. Some of the tin 2 absorbs and it goes there. And what it means is if I scan faster and faster, I can't see anything because all these surface waves get bigger and bigger and complicate the attempt at looking at anything on the diffusion waves. Now, if I want to do the SECM, then I do the calibration curve as I showed you here. That is, as I get closer and closer together, the CVs for a reaction get bigger and bigger and bigger because the current is getting bigger and bigger. And I can get an exact calibration of the distance with the current level. Now, if I take a very stable compound like ferrocene methanol, and I look at the voltammogram at the tip. So here's the oxidation of ferrocene methanol at the tip. Nice one. And at the same time, I collect that at the bottom electrode. So here's the voltammetry at the substrate, the reduction. Then I get a nice symmetrical figure. The current at the tip equals the current at the substrate because the collection efficiency, N, is 100%. I substrate over I tip. This is just showing that if you try to do cyclic, you see there's these surface waves get bigger and bigger and bigger here and distort the voltammogram. And also shows that, in fact, as you start to plot this, it goes as proportional to the scan rate, not the square root of the scan rate. So here's now the experiment with tin. Now with tin, I'm going to do the same thing, but I'm going to try to collect an intermediate here and find that intermediate and compare that to collecting the product, tin 2. So this is the voltammogram, and I can do an experiment at 2 places. I'm going to always go with my tip and reduce tin 4 to tin 2. But I can put my substrate at different potentials. If I put my substrate over here, where tin 2 goes to tin 4, I'll get the same thing I saw as with ferrocene methanol. So I get the reduction wave here and the oxidation wave down here. And it's essentially 100% collection efficiency. However, if I put the potential at the foot of this reduction wave, now I'm not going to collect any tin 2. I'm not a potential where I can collect tin 2, but if there is any intermediate formed that's oxidized in here, I'll find that. And so I compare, and those are the smaller guys over here. In other words, if I put the potential here, I can collect some of that. And so all the experiments I'll now show you are ones at the potential of this arrow. I'm going to collect, I take tin 4, reduce it, and see who do I get at this potential, not out here. Who can I oxidize over here at a much less positive potential? And I can measure that current as a function of distance and plot this. And so here is a plot of that current as a function of distance. So if I'm far away, my my collection efficiency is 0. I don't see anybody at the substrate at big distances. But as I get closer and closer, I start to collect it here. And the X's are a digital simulation of that process, which gives you a rate constant for the disproportionation of something like 10 to the 5th. So it's a pretty fast reaction, 10 to the 5th moles to the minus 1, seconds to the minus 1. So a pretty fast reaction, but I can calculate it. I can find it, and I submit that this is tin 3 that we're finding. So what's happening then in the process, we think, is this. So let's write this as the so-called square scheme. So as we go across left to right, we're adding electrons. So this is an adding electron thing. As we go up and down, we're losing bromides. So this is a bromide number. So bromide goes 6, 5, 4. Electrons go add 1, add 2. Start here at tin 4 and end up at tin 2. So what do we think is the process if we try to simulate it? And I'll give you some numbers, but I can't go through the whole story. So I start here at tin 4. I add an electron. As soon as I add an electron, I lose a bromide. And this is this intermediate species at the crossing point, which is the tin 3 Br5, which is disproportionating. Then this one will disproportionate, but will also add an electron, because tin 3 can add an electron, and then that loses another bromide and goes up to the tin 4. So you go in steps, electron, bromide loss, electron, bromide loss, and we do that. If you play around with this and do all the stuff electrochemists spend their time doing, you can guess around rate constants. The basic message here is that the loss of bromide is very favorable. You add an electron, it wants to lose a bromide, which is not unexpected, and it's pretty fast. And also, these electron transfer reactions are pretty fast. And so these outer sphere reactions, as one electron transfers, look like they're pretty fast reactions. One's got to have to read the whole paper to really understand this. So I think what's the message here? So the message is, I think, by using techniques like scanning electrochemical microscopy, you can go now to very fast homogeneous reactions and really diagnose them pretty well. The secret is, I think, I talked about it as a secret of steady state, but a more easy way of understanding why this works is that in cyclic voltammetry, you generate something and then analyze it at the same electrode. In other words, when I scan one way, I generate the product, then I have to scan back to find it. And that's tricky. It's tricky to generate and find at one electrode. In SECM, you're doing this at 2 different electrodes. And so you generate at one electrode, but you find it at the other. And I can kind of independently control these guys, and then they don't cross-talk or cross-couple in this series. How's my time? So let me give credit to the guy who did most of this work in a rather wistful picture. This is Jinho Chang. Jinho is a graduate student, just got his PhD, and is currently going to Illinois to postdoc. This was supported in the early stages by the Center for Electrochemistry, which is a center we have at the University of Texas, which Dick is an important part of, which tries to promote electrochemistry. And it was also supported by this global climate and energy project from Stanford University, GCEP. Their interest was not in any of what I'm talking about today, but in making flow batteries and trying to use these kind of concepts to improve the batteries, and also the National Science Foundation. Thank you very much.
We have time for a question or two.
So often in proton-coupled electron transfer, people assume the proton transfers are really fast and the electron transfers are slow.
They are really fast. I mean, both of them are really fast is what this seems to turn out. But the bromide reactions are very fast. Yeah, yeah. I mean, there's another part of this talk which I threw out because, you know, one obvious question which somebody is probably going to raise is tin 4, tin 2 looks pretty lousy as a redox couple for a battery. But in fact, if you go up to 9 molar or 10 molar bromide, that really collapses a lot. So yeah, bromide really helps in that. George?
Can I follow up on that question? I mean, this is a fantastically interesting talk, really picking things apart. But there's yet another step, which is, you know, you can make a case for a tin 3 bromide, but then the electron comes in and the bromide comes off. And are there yet further layers of intermediates, you know, partially default solvated species, you know, Rydberg states, I don't know what else along that pathway?
Sure. I mean, I think the problem in electrochemistry is that everything is very complicated. I mean, that's certainly the bywords of electrochemistry. And so, yes, there are going to be all kinds of, you got to lose water. Is there a state when something comes in and the water goes out, and is it concerted, and how fast are they doing it? And so those are all the questions which I'll not live to see answered, but which will be answered, I think, eventually.
So you and I spend our life studying mechanisms, and at the end we know less than when we started.
That's right. Absolutely.
Okay, last question.
Following the question by George, uses alliance theory applications for each with the loss of the bromide is through that you make this intermediate.
As a real intermediate, not concerted. Yes, yes, that's right.
You cannot demonstrate that it's coherent.
That's right.
Now, my question was, could you think that it could go down, like for example, when you make the cycle with peroxide xylon, in order to catch this one before it splits out the bromide?
Well, it's a question of distance, but really, you know, by the time you get to 10 nanometer distance, we're pushing really hard to try to do that now. We can do 100 nanometers, get to 10 nanometers. That's going to be the end of the line, because once you get much below that, you're going to start tunneling. And now the current goes tunneling current, and all bets are off.
So it's just not the same reason, but the same limitation as the neutron pacific.
Yeah, but at a different regime of time.